Hi everyone, my name is Nan. I work for Mott MacDonald. I joined Mott MacDonald about 5 years ago. Originally come from the UK and relocated in Bangkok. I absolutely love it, especially during the COVID. It was fun to be here. Um, and Oh, first of all, thanks very much for inviting us. You went Vortex to give a bit of a presentation and a bit of a talk this afternoon. So, well, the topic is hopefully it's self-explanatory. Sorry, yeah, I can hear my voice a lot better now. Okay, sorry, I should be okay, isn't it? Yeah, so the reason I was thinking of giving this presentation was that after working with, I mean, myself working with various developers in the past 15, 17 years or so, um, one thing that we noticed from working with various stakeholders in the past was that, especially for the early stage of wind farm development, um, it's easier for people to notice that look, this site got 6.5 meters per second wind speed, and Malaysia, I don't know, 5 meters per second bad site, 7 meters per second great site, but is that sufficient to decide whether that's a good site or not? So and I think our thought is perhaps not really. I think the not only just wind speed, but also the wind speed distribution might be a more of a key factor to consider if we're looking at finance and everything. So yeah, so without much further ado, on the very first topic, very first cover sheet, and I'll probably moving forward to the actual content. So maybe using this is a better way to do it. Sorry, this is from my commercial team. It's not my fault. So I'll go through that very, very quickly within 2 minutes if anybody wanted to time that. So who are we? And I've talked to myself. Who are Mott MacDonald? We're in the forefront of renewable energy for over 100 years, much older than myself. Um, we've got a business across the globe, especially in this area where we're sitting at the moment. And our energy, in particular sectors, we provide technical advisory, honors, engineering, detailed design, project, and digital management. And awards, I'm not going to go through that. I don't remember either. And all these sectors in energy, in particular renewables, hydro, solar, and the bits we really love, wind power and cables, and that's all we're doing. And that's going to the next one. Not really going to any of these. So this is our service for energy, wind energy yield assessment service. We, particularly myself and my team, provide going through feasibility, the early stage feasibility studies through operation and repowering projects. And my team, mostly based in Bangkok, including myself, about 10-ish wind analysts, a couple of them here with me. In case I can't answer your questions, they will as well. And um, what was it? Yeah, okay. So we've been working on more than 20 years on renewable energy in this region with over 100, sorry, not 100, 500, I think, wind farm projects. We know exactly, understand the challenges facing all different stakeholders. Right, I'm going to this one, this one. Oh, agenda, that's good. So actually going to the main point of the talk today. So we'll do a bit of introduction in a minute, and the methodology, how we got to our result on the case study, where we'll talk through, I'll probably just walk through a few simple projects, well, not simple projects. I'll try to make it simple. Um, in the past from our experience, including onshore, offshore, and nearshore projects, to see how the wind distribution affects the energy yield assessment, or actually energy yield results, and coming with a bit of conclusions. It's not really conclusion, but kind of, I say, summary of what we've seen from our experience, and actually a kind of a topic to discuss, really open to the floor, if you like, and Q&A, obviously. Right. Okay. Introduction. I'm going back to here. Right. So, as I said, perhaps a little bit of common misunderstanding, maybe, or misconception that a high wind speed for a wind farm site always leads to a high energy yield, which is perhaps unfortunately not always true, and um, and we will go into a bit of detail in the next few slides. But it's the other parameters that goes into the energy yield assessment, including the bits that will focus today, which is the wind frequency distribution. Obviously, there's other, wind rows and everything, but the topic we focus today is on the frequency part of it. Right. Very first, or let's say fundamental principle. If I don't know how many of us sort of familiar with sorry, maybe this presentation is getting a bit drier and drier for next 5-10 minutes, and this is the very first one. So, so do you have the light? Not really. I don't know. But anyway, the red curvy line is just a power curve of a random generic power generic turbine, and the frequency histogram is this wind distribution from a site, and maybe go to here. Yeah, that's better. So the gross energy for a site, let's say, is actually the area covered underneath the power curve overlapping with the histogram. So basically, as you can see, the gross energy is kind of determined by the power curve, obviously, and the area, not just the wind speed. So most of the wind speed is over there, but the actual operating wind speed that actually works is underneath that. So therefore, okay, there's no therefore. All right, and then okay, it's a case study from, let's just say, nearshore, onshore, offshore projects we've done. We've seen that different distribution can be caused by a few factors, general terrain complexity, especially relevant for onshore complex sites, localized effects at specific locations, and even the period of measurement. So, this year might be very, very different from next year, for example. And we did a bit of an investigation ourselves, so we'll show you the results. Maybe the next one is hopefully not introduction again. Right, sorry. Yeah, methodology. So it looks a lot, but actually how we got to our results, which we'll show you in a minute, was actually we just follow the usual EYA process, starting from data analysis with short-term measurement inputs after screening, calibration, synthesis, whatsoever, and we'll then go into long-term correction and vertical extrapolation if the measurement height was a bit different from hub height. And so the output of the first bit was to get long-term adjusted wind speed and distribution at hub height from probably the measurement locations, and then went into together with other outputs, together with other inputs such as power curve and wind flow modeling parameters, and obviously the layouts like the list, and to get the output of gross energy yield across the site. And our result was to look at the comparison between long-term wind speed distribution and the corresponding gross yield to see what matters, basically. Okay, moving on. Right, case study number one. So we're actually going to come into the slightly more exciting, slightly more interesting part of it. So number one, projects. Where is it? Right. So it's a nearshore one, and so the big background, the setup, or let's say the measurement campaign setup was consisting of a pair of Mars and LiDAR. Thanks very much, Vincent, for introducing what LiDAR was. We didn't talk to each other before this presentation, I'll show you. Um, and dual scanning LiDAR. I think we didn't show that here. Basically, the setup of dual scanning LiDAR was there are two of them, obviously. That's what was called dual. Um, one in the north and one in the south of the master LiDAR locations. But the actual scanning point, or let's say the actual measurement point, was somewhere there inside of a project boundary in offshore environment. So okay, so each one of the measurement had probably about 1 year of data measured. So yeah, a bit of wind rows to see what's it like from each location, and basically what we have observed was that was in the next slide. So so offshore location, no problem at all. But for the onshore location where the mast and LiDAR were, they were actually located right next to a hill in the east, and with a bit of forestry where the green bit is. So right to the east side of the mast, there was about 30 meter, oh, thanks, 30 meter, 50 meters of higher elevation than the mast. So bearing that in mind was quite an important bit. And the mast was measuring up to 60 meters only. Right, there you go. So that's the distribution we've seen or work out actually from each of the measurement points. The gray histogram came from the dual scanning LiDAR, if you remember, it's offshore, and the master was the red curvy line onshore, and then the vertical LiDAR is right next to the mast. And Vortex, thanks, Emily. And 30 years, Vortex data just gives us a kind of a comparison for comparison reasons. As you can probably tell, there's a very different distribution at the mast location, very different from the rest of it. And what we think was because the location of that mast, and especially the measurement height of it, it was not completely exposed to the wind, particularly coming from the east side, where was kind of there was a bit of obstacles in the east, where the higher level of hills and the trees were. So, and in the numerical table results, um, so in the first top table, let's say, and the LiDAR, vertical LiDAR, was measuring about -2% lower than wind speed than the Mars. But however, the gross yields came from using LiDAR was actually 1% higher than that. So even more difference that we've seen was to compare with the dual scanning LiDAR and MAST. So even the MAST was almost like comparable with a dual scanning LiDAR, about -1% in terms of wind speed difference, which is pretty much like nothing. And if we use the MapMaster data, the gross energy yield for the whole site would have been -5% lower than using the dual scanning LiDAR. So a little bit of notes here. Yeah, we think the topographic factor from the hills in the east and the trees from the east again in the surrounding areas might have caused the difference in wind speed and energy estimates using the master. So I mean, as the wind analyst, or in this particular case, it may be easier. Well, it's probably not very difficult to see that dual scanning LiDAR is probably more relevant, let's say more representative of the offshore um, environment offshore projects. But um, yeah, but as you know, Vincent just said, the LiDAR needs a bit of validation and usually bears a little bit higher uncertainty in terms of measurement than the MatMast. So it's a bit of a balance of or consideration of overall uncertainty when it comes to deciding which one to be used as your primary measurement. Right. Okay. Probably not gonna go through that. Okay. So this case study number 2. Um, this is not real site, so you don't have to take pictures of a nice holiday destination here. So four masts, very complex site basically, and multiple years of data available from each mast. And basically what we're saying here is everything looks very different in terms of distribution, and you can see from the numerical result there, even though with 3 km away from each other, M1 and M2, in terms of wind speed was only 5% and gross yield at nearby turbine, but overall, for using M2 mast to predict the whole site in terms of gross yields, and you will get like 58% higher than using M1, which is horrendous. It's just no, don't do that, basically. And a similar thing we can see from M3, M4. So it comes to the fact that you got to decide, like we got to decide that which one, or the master association, which one to go with, because the sensitivity, let's say, using different measurement points or measurement locations, is too huge to take any risks at this point. And as I said, depending on the master association strategy, you might looking at somewhere between 0 to 58% in gross energy only. Right. How are we looking at time? Should be okay, isn't it? Right. And okay, so last one, offshore one, exciting. Floating LiDAR. Again, this is not the real site. Something like that, I think. So yeah, so Marvin, you should like this. Vortex LIS data, I know is kind of being replaced by more advanced products. It's only because we looked at this in 2022, so we didn't have times at a time. So the measurement campaign here we had was about 1 year measurement from floating LiDAR, which was very costly to our client, measuring from the end of 2024 to the end of 2025. And what we had also at the same time was a Vortex LES data for 1 year, concurrent period with the measurement, and also 2022 to 2023. Yes, comparison, have a guess, Marvin. Products, how different is that? Yeah, so this all these plots were kind of long-term adjusted already, right? Don't worry, your data is great. Um, so what was it? Right. Again, the gray area, sorry, the grid histogram, floating LiDAR distribution, and 20 years long-term reanalysis Euro 5 data, which is a free data available to us, just for comparison purposes, that's all. And Vortex LES concurrent period with floating LiDAR looks all right to me, not too bad at all. Following the similar trends. And LES data 2022 to 2023, what's going on? It's just completely different from the rest of the data set, wasn't it? Yeah, so we gathered, and you can, and again, on the right, the numerical results. Comparing LES 2022 to 2023 with the actual measurements and the other year, low wind speed, -7%, much higher gross energy yield using that. So imagine that's what happened to us as well. That back in 2023, we didn't have anything else, like all these measurements or anything. What are you going to do? I mean, there's only just a vortex data. There you go. Maybe. And some sort of benchmark experience across the site, across the region. And we looked at that, thinking that might be okay. But it turns out it was, we used that and compared to what happened in reality in 2024, 2025, probably ended up with a several percentage overestimation compared to what's happening now using measurement. So I think that's kind of the thing, that the kind of questions that kind of, or challenge that we are facing each day. That once you got limited information, particularly at early stage of development, what are you going to do to validate what you're seeing? And essentially, we looked at all the available data set to us. We think that the distribution of that year, 2023, was very different from the rest of the years for the region. And in fact, the measurement in 2025 was more comparable with what we think it should be. But given that's what we think it should be, is a bit of a subjective decision as well. So again, I mean, it's not really our conclusion, but just kind of thinking of ours is that usually 1 year of measurement is recommended, or let's say the minimum requirement for bankable UAA. But in fact, or in reality, whether that's sufficient or not. If you ended up had 1 year measurement in 2023, you will likely to overestimate energy yields. So okay, so next one. Is anything else? Right. Okay. So the summary of these case studies. Wind frequency distribution. So we think the wind speed alone does not fully describe wind's resource quality that well, and the frequency distribution results in very different energy yield figure, even with the same mean wind speed. And so it's basically just a bit of lesson learned from each of the case studies we had just talked about. Local axle effects. Remember that master LiDAR overshadowed by by the trees and then higher grounds. And case number 2 was more of like the completely complex terrain. How many measurement campaign design? How much design are you thinking of? You're gonna do to kind of cover or to capture the localized effect by the complex terrain and trees, heavy trees actually. To a certain extent, sort of considering additional measurement to capture localized wind regime. And obviously that's, again, to kind of considering technical gain versus economical gain as well, is a bit of optimal thinking, optimal solution that you've got to think about. The last bit was the period, and there's nothing we can do about the periods that we're measuring. I mean, it's measurement is a measurement, but whether if you discover, or let's say find out as being a bit slightly different, you may prolong extend the measurements if you need to be, but the key is to get it done at an early stage rather than leaving to the later stage to see, oh wow, the energy yield is actually we thought was that, and it was actually here. So okay, so I think we're probably coming to the very last of the slides. Again, it's almost like the repeat of what I just talked about. So throughout the talks. So do not rely on me with speed only, and find a representative locations for your measurements, and thinking of your mass association strategy. Or by mass, we really mean measurement. It doesn't have to be mass. See that LiDAR could be bankable at some point in the future. And um, measurement period, yeah, it's the tricky one. And I know the developers, or let's say business development teams in developers, that they wouldn't like spend much money. We like to, but there's a balance between uh, measurement and economic gain, reduce of uncertainty, make everybody happy, lenders happy, we're happy. Yeah, so that's it. Thanks very much. Was there any Q&A? Q. Nice. Right.
Easy one, easy one.
Okay.
Thank you.
No,
So
quite difficult ones anyway.
the typical wind distribution that we see is a Y bull, so this curve.
Mm.
But in the case studies that you presented, it doesn't look like a Y bull. So I just wondering if, in your experience in the region, these case studies are like special case, or you see this in almost every project, or these case studies are only for one country, one specific country, or you see this in other countries as well?
All these three projects, they're not in the same country. No, different countries, and I don't think they're project specific, and we don't tend to use Weibull anymore. Basically, we just follow the measured distribution. That's the whole point of it, because rarely the cases that follow Weibull anymore, essentially. So we use measured distribute the actual measured data to um to represent the from let's say not represent to extrapolate from measurement to turbine locations. Yeah. Yeah. At the back.
Um, you said that you saw 2 years that were very different, 22
Yeah,
and
this one, that one.
yeah. So have you looked for a long time series to see which one of those 2 years it's the rare? It's the, I mean, if you are gonna make a long-term correction,
Yeah.
your measurement period should be on the normal climatology.
Yeah.
So did you figure out which, if your measurement campaign was in the more typical climatology or out of it?
Yeah, that's what I said, because all these distributions already long-term corrected, and the the 20-year long-term reanalysis, the era 5 data, was the blue dash line, um, kind of gives well, I put that just for reference, really. So um, let's say the vortex 2025 and actual the measurement in 2025. And while I said this 2020, well, it seems to be 1 year, but it's already long-term corrected, and that's what it is from the measurement. Yeah. Yeah, sorry, I should have made that clear, that when I say 1 year, it's not just the short-term distribution, but it's already been long-term corrected. Everything was being long-term corrected. Even so, we've seen that much of difference, basically. Yeah.
So is there any more questions you'd like to ask Nan? Okay. Well, not sort of questions, but rather I think the question was asked about the distribution.
Yeah.
So I know that you have corrected for the long-term wind speed, but it's the shape of it is
Yeah.
actually, I think, the main point here.
Yeah.
My guess is that is Taiwan.
We didn't correct it for the wind speed. I say that the wind speed was a bit low. So this distribution was not normalized to one single wind speed.
Yeah. That's understandable. But
It
so
was from Taiwan, yes.
yeah,
Yeah.
I recognize that from the pattern.
Yeah.
But I think my comment here is that you have 2 years of reanalysis data. Basically, the one you have with the measurement period matches quite closely with the reanalysis data.
Yeah.
So what you see here is actually a double Weibull. So you have 2 wind seasons of the high and low wind season. So you have double Weibull stacked on top of each other. So that's why you get this distribution. What you see on the previous year is actually sort of a lower wind speed year. So the Weibull get shift quite closer to each other.
Yeah.
So I guess if you really want to determine the, what's the actual shape should be, maybe you should compare the distribution on the, the low wind speed months against historical low wind speed months and the high wind speed months against the high wind speed months.
Yeah.
So maybe it's somewhere in between.
Yeah. Yeah, one could be somewhere in between. It could be this and that, and somewhere in between. And if you had a 2023, I mean, if you done this exercise, let's say in 2023, what would you do? I mean, obviously without much information of the later years, if you didn't have much of information from around the region, yes, we did obviously, and obviously that we did. To be honest, we did notice that what was going on was like, wow, there's 7% lower, like 10% or 7% lower in wind speed, but the yield was not that different. So and at the time we thought, right, maybe maybe not, and ultimately it as I said, ultimately it's not the wind speed that mattered too much, and we were aiming for get the reasonable gross yields or something. So that the decision we took at the time was that the gross yield wasn't too bad compared to other benchmark we have got, and therefore we still went for this one. But obviously, when after we got a 2025 data, and even though it's plus or minus single digit difference, it still mattered um, to the finance team or to the development team from our client side. Why is it, why is, why did we predict something 4%, 3% higher before? Now we're having a bit of a drop. And then also that the developers would, it's offshore projects, and everything single bit matters a lot of millions of trillions of dollars, and then so any single drop was raised, but so as well the point I was trying to make that at early stage you got to be careful with I mean we got to be careful with what we see and what we think it would be to kind of to avoid future disappointment. Now they were not extremely happy with a couple of percentage drop, basically. That's what I'm saying.
Yeah, exactly. So I think the 1 year minimum is really the minimum. But I think we tend to recommend like 2 or more years. So you don't get this sort of things happening.
Yeah. Times, so we used to only had just 1 year of vortex, but now I think you probably had more than 1 year of 10-minute high resolution data. So I'll leave that to next sessions for vortex to kind of highlight their products.